Thank you all for logging in. As he said, I'm Andrew Damuller, and I will be presenting on lateral load analysis considering the soil structure interaction. Start off here with an overview. So first thing we'll be looking at is an introduction, kind of what this topic is about and why we're discussing it. Then I'll discuss three methods that are commonly used to account for soil structure interaction for static loads. That is depth to fixity, elastic springs at the column base, and including column and caisson with soil springs within the finite element model. I'll go into more detail about integrating soil springs within the finite element model using MIDAS Civil, and then I'll jump into a case study, which will be a 3-span reinforced concrete flume. So in designing structure, the interaction of the structure with the soil is obviously an important consideration. Pretty much everything we design is going to be founded on some type of soil, and it's important to realize the interaction between the structure and that soil, right? So in many cases, the absolute and relative stiffness of the soil can have a significant impact on the forces experienced by the substructure elements, and the relative stiffness of the soil from one substructure element to another is also important, since it influences where the location of the point of zero thermal movement is. So in general, the point of zero thermal movement moves towards stiffer elements. So that's going to be your shorter piers, or if your piers are about the same height, then your soil stiffness is going to have a significant impact on where that the center thermal movement lies. The location of the point of zero thermal movement is important in determining the movement at each substructure element. Obviously, we want to know that at the ends of the bridge where we have our expansion joints. We need to have a feel for what kind of expansion and contraction we should expect. Also, for our piers and abutments, we're going to have loads induced, assuming that we're fixed along the length of the structure. The piers and abutments are going to experience a force as they are asked to move. So they have some stiffness, so any movement is going to induce a force within the substructure elements. So three common methods for dealing with static soil structure interaction are to use the depth to fixity, elastic springs at the column base, and the soil springs within a finite element model. So I'm going to go briefly through all three of these and then go into a little more detail about implementing soil springs within your model. So first one I'll discuss is the depth to fixity. The effect of the soil can be approximated by including some portion of the caisson with hopes of kind of mirroring the actual behavior of the substructure element within the soil. There's a couple ways that we can approximate what that depth to fixity is. The first that I'll discuss is to determine it analytically. One way of doing this is to determine the length of caisson that's required to cause the pile head translation and rotation to equal that given by an analysis of the pile's interaction with the soil. So compare what's going on in your finite element model with what you're doing in L-pile. Complete convergence of both terms may not be possible, so you may need to compromise. Since we are approximating the caisson or pile as a fixed element, the shape of that is not going to take the same shape as your substructure element within the soil, and therefore you're not necessarily going to find a single length that's going to allow you to match within a tight convergence for both your lateral translation and rotation. So you can compromise, say it's good enough if you're within 5 or 10% for both parameters. Kind of an even greater simplification from there is to use an empirically based equation AASHTO provides equations in the commentary of Chapter 7, Section 7.3.13.4-1 and 2. One of those is for clay soils, one for sandy soils. But that is definitely a very approximate depth to fixity. That's only taking into account kind of one soil property over the entire depth of what you're using as the depth to fixity. There's really no accommodation in there for putting in different soil layers. But it is a good starting place. So a couple advantages to using the depth to fixity is it's relatively simple to implement. You're just basically calling your column and caisson system to you're approximating it as a fixed cantilever. You can obtain reasonably accurate structural behavior so long as you can get good agreement between what your finite element model is doing with the depth to fixity and what your more soil analysis type program such as Alpile is doing. A few disadvantages. You do need to go through iterations in order to obtain a reasonable depth to fixity. Convergence can only reliably be attained for one parameter at a time. Like I was mentioning earlier, you would need, if you wanted to match perfectly, you would need a different depth to fixity for translation in both the longitudinal and transverse direction and their associated rotations as well. Another disadvantage is you're really not getting any useful information about the caisson itself and the loads that it's experiencing. You're calling it a fixed cantilever, so your maximum moment and shear is going to occur at the bottom of what you're calling your depth to fixity, which is not a whole lot like what the reality is. So kind of throw out those results once you get below the bottom of the column. And then you would go into Alpile or something similar to determine what your forces are within the substructure element. Another method is to use elastic springs at the column base. So you can apply these springs. You can specify the spring stiffness for each relevant degree of freedom. So in general, that's going to be your longitudinal and transverse, translation, and rotations. So you got kind of 4 values there that are, I guess, most meaningful in your lateral analysis. This analysis can be an improvement over analysis using depth to fixity because the stiffness of the spring can be specified separately for each degree of freedom. So you can achieve convergence between your kind of Alpile results and your finite element model just by tinkering with each of those values independently. This method also requires iteration since the translation and rotation is not necessarily linear with respect to the lateral load. A couple advantages. You may get a more realistic model using this than if you were just to use the depth to fixity. And the spring stiffnesses can be specified for each degree of freedom. A couple disadvantages are that iteration is required between your finite element model and the soil structure analysis software, and no information is available concerning the shear and moment within the pile or caisson. So just like when we're using the other method, the depth of fixity, we are not obtaining any useful information about the substructure element itself, or the deep foundation element itself, the pile or the caisson. So now a little description of soil springs within a finite element model. To avoid the iteration involved with the other 2 methods, soil springs can be integrated directly into the finite element model. You can use either elastic springs or nonlinear springs, I guess multilinear springs in MIDAS Civil, and those you would be getting from your geotech, or you could start off and get the required parameters from Alpile. MIDAS Civil makes this simple. Using the surface spring feature, requires only the soil subgrade modulus if you're going to go the elastic spring route. Using this method, the entire pile and caisson length can be entered along with corresponding surface springs representing the soil. One advantage here is that you get the shear and moment along the pile or caisson directly from your finite element model. So we are getting useful information about that deep foundation element. And the structural behavior, including soil structure interaction, is fully considered. You need to ensure that an adequate number of elements are implemented to ensure that your peak shear and moment are captured. You can have a relatively high shear and moment gradient, especially near the top of the pile. And in order to capture your maximum value, you need to make sure that you have an adequate number of elements in that area. So a couple advantages. No iteration is required, especially if you're just taking values that the geotech gives you and use those as your modulus of subgrade reaction. That's going to be a constant, and you can use that throughout your model. The caisson shear and moment can be obtained directly from your finite element model, and the accuracy of the structural model can be at least as good as with the other two options. A couple disadvantages. It may require somewhat more work to develop the model, especially if you feel like you need a little more accuracy and you go into developing multilinear springs for your soil springs. It's going to take a little more work to determine those and to enter them into the system. And you need to know the modulus of subgrade reaction for the various soil strata. So that's something, again, you would either ask your geotech to give you representative values for that, or you can use the soil profile that's given and obtain your subgrade reaction from a program such as LPile. In MIDAS Civil, in particular, when you're utilizing soil springs, the structural model is created, either the substructure of interest, or you can even throw your entire structure as a single model, including the deep foundation. The boundary conditions for lateral loading are then created using the surface spring option under boundaries. I'll just point that out real quick on the next slide. And within the surface spring dialog box, the type of element upon which the soil spring is to be applied can be chosen, along with the type of spring desired. So you can have a surface spring or a point spring. You can have linear elastic, compression only, tension only, or you can define a multilinear type spring. The required parameters can then be entered, including the modulus of subgrade reaction. So just real quick, here's, if you have MIDAS and use it, you would be under the boundary tab, and just under surface spring is where we find these options. And I'll bring this up in a minute when we're doing the case study. Once the model and boundary conditions have been entered, the loading can be applied and results obtained. So some of the results you may be interested in are the point of zero thermal movement and the moments along the columns and your deep foundation elements. All these can be pulled out directly for your various load cases. You can create load combinations within the program, and it'll spit out your factored loads for you. Just real quick, before I used the results directly from MIDAS Civil, I verified the accuracy of the calculations it was doing. So using elastic static lateral subgrade modulus values given in the geotechnical report, I entered those into LPile, specifying a linear elastic type input, and did the same thing within the finite element model and MIDAS Civil, and below shows how those compare, which if you take a look at it, and they match quite well. So now I'll discuss what I'm going to show you in the case study. So I have a simple case study. Figure that would be appropriate for this for this type of presentation, just so it can kind of show a little more detail the aspect that I'm focusing on. So I have a flume just shy of 200 feet. It's a 3-span structure, 3 main spans with 7-foot cantilevers on each end. The span lengths, the major span lengths are 61 feet, 65 foot 2, that might be a typo, 60 and 61 foot. And these span lengths were chosen to work around existing drilled shafts. They're not necessarily ideal, but it's what we can make work. The superstructure is an 8-foot deep reinforced concrete tub girder. The piers were designed such that most of the superstructure loads were applied directly to the columns, so the columns were placed directly below the webs of the superstructure element. We have 42-inch diameter columns, 4-foot diameter caissons, and a variable soil profile is considered. Simplified it a little bit for this presentation, and lateral loads were applied as per AASHTO LRFD specifications. I think in this case study I'm really only showing dead wind and thermal, just to show a couple loads within the model. So here's what we have. This shows our overall length, our span lengths. I think I had a typo on that prior slide. I was calling it 65 foot something instead of 63 foot 8. Then we have our 7-foot overhangs, and this is the cross section of the superstructure element. So here we are carrying water through this thing. It's 17 feet wide and 7 foot tall. And we have these wings up the top, partly to resist the negative moment, since this is a continuous structure. And those flanges also double as a walkway for maintenance workers along this ditch. Alright, so now I'll jump out of my PowerPoint and get going on the case study. So here I'm just going to kind of build it from scratch. Towards the end I'm going to skip a little bit of stuff just for the sake of time. And well, here we go. So first thing I do when I get going in one of these models is I create my properties. I have 5 KSI concrete for the superstructure and for the columns and piers and all that. I also have 4 KSI concrete for the caisson. They also have our section properties. So I'm going to have user-defined solid round. I'm going to call this my column with a diameter of 3.5 feet. I'm also going to define my caisson section property as a solid round shape with a 4-foot diameter. I'm going to have the pile cap, which is simply a rectangular cross-section, solid rectangle, with a height of 2 feet and a width of 4 feet. And the superstructure is not something that's readily defined in here. It's kind of a unique shape, at least relative to what's commonly used in a bridge. So I'm going to define that shape using coordinates. So first we'll call it the Flume superstructure. Alright, so we just have our first point. I'm going to use relative coordinates to simplify things a bit. What's going on? So starting at 0, and then we're going to move 3 feet to the right, 7 foot down, 17 feet to the right, 7 feet up, 3 feet to the right, a foot down, 2 feet to the left, 7 feet, oops, 7 feet down, 19 feet to the left, 7 feet up, and 2 feet to the left. So that is the cross-section that was used for this superstructure. So we're holding the water here in the middle, and this is our, our structural shape. Need a couple other things defined before the program kind of lets us use it. So T1 is the thickness of kind of our top flange. That's a foot. Thickness of our bottom flange, T2, is a foot. B sub T, center to web of center web, is 18 feet. HT from center bottom flange, center top of flange, is 7 feet. Thickness for torsion is a foot. I'm going to let the program auto-calculate Q sub Y and define my Z1 and Z3 positions, so just at the bottom and top of the cross-section. So just above the bottom and just below the top. And now we have a defined cross-section. We can display the centroid and where our 4 extreme points are. In here, we can take a look at our properties that were calculated based on the coordinates that were entered into the program just a minute ago. We find that the distance from the centroid of this shape to the bottom of the shape is the z value of 3 and 4. So Z4 is minus 2.77. Z3 minus 2.77. So we're 2.77 feet from the bottom of the bottom flange to the centroid of this shape. All right, so now we have all of our definitions done. So we can start filling some nodes in. So we're going to create a node. The first pier is at 7 feet. The columns are 18 feet apart, so 9 feet in each direction. We're going to center this bridge at a value of y equals 0. So we have that. We can do the same thing for the bottom of the other column. Now we can copy these nodes 16 feet vertically. So that's from the bottom of the column to the center of the pier cap. So we apply that. We also want to define the extreme points of the pier cap itself. So we're going to go 2.5 feet from the center of the column. So since it's I guess it's just shy of a 4-foot diameter column, we have some extra room there. We have some overhang of this pier cap. All right, going to do the same thing on the other side, 2.5 feet, and we're going to put a node out in the center. So we're going to go -9. So this node in the center is in place for the superstructure. That's where we're going to tie the superstructure in to the substructure. This is just kind of a stick model in terms of the superstructure. So we're going to have to use some boundary condition to tie that girder to the substructure elements. All right, so now we can create some elements. We can create our column using 5 KSI concrete here and here. We can also define our, if that meant to be pier cap rather than pile cap, but I'm sure you'll forgive me. All right, so now we have one of our piers stands the caissons put together. Those elements are a little ridiculous. You wouldn't just have one element from top to bottom of the caisson, or column rather. So we will divide those up. Let's see. Take a look at my notes. Divide the column. I'm attempting to keep element size pretty close to consistent throughout the entire model. So we're going to split that up into 4 pieces. we're going to split each of these segments of the pier cap into 3 segments. All right, so now it looks like something we could use. So we can go ahead and copy that. We're going to translate the elements, so that will bring the members and the nodes together. We're going to copy that 61 feet. Going to grab the most recently created items using this button here, and then copy again. Where'd we go? 63 and 8 inches. And our final pier will be 61 feet from pier 3. So here's what we have so far. At this point, we can create some structure groups. I won't quite divvy those out yet because I want to include the caissons in that. But we can create them. So we have pier 1, add pier 2, 3, 4, and superstructure. All right, so now we can go ahead and start putting in our substructure. So we have the nodes at the bottom of each of our columns. Here, let's do this, rotate things a little bit so I can grab things easier. So I'm going to copy using the translate function. I'm going to copy those nodes down 10.2 feet. So that's the bottom of the first soil strata. So from 0 to 10.2 feet, we have approximately the same soil. We're going to go down another 14 feet for the next soil strata. Eight feet for the next. And 11.8 for the final. All right, so there are our nodes. Now we can create our caissons. Let's see, node element, create elements. We're going to use the lower quality or the lower strength concrete for the caissons, and our caisson cross section. Define it as such. Again, we are going to need to split these up, and then we can implement the soil springs. Just while I'm thinking about it, we're going to throw in a vertical rigid support at the bottom of these caissons. That's kind of useful to have just as rigid support because that's the reaction that you're kind of looking for when you want to design your caisson for the geotechnical capacity. All right, so throw those in. Now we're going to split up these caissons using the element divide. I'm going to divide the top soil strata into 4 segments. The next into 5. Next into 3. And the bottom soil strata into 4 segments. So the reason for breaking that up differently for each one is just there's a different length, and I'm trying to keep a fairly consistent element length as I go down the length of the caisson. All right, so now at this point we can get into kind of what you're here for, right? The soil structure interaction portion of this model. So we're going to grab those elements from node 1 to node 69 to node 70 and put in our surface spring. You can define boundary groups. That can become helpful as you're trying to sort things out later. I'm going to skip that in this case. You can either convert your surface spring to a nodal spring, or you can use a distributed spring. So when you're using a nodal spring, you can either use a point spring or an elastic link. I'm going to go with the point spring. The element type to which we're applying these springs is a frame rather than some sort of plate or some sort of solid element. So we'll select frame, and the width of our caisson is 4 feet. Within this type, we have the choice of linear, compression-only, or tension-only elements. I'm just choosing linear because we're going to have soil on both sides of this thing. So if it tries to go one way, it's going to be resisted by the soil on that, on the resisting side. If it's trying to go the other direction, there's still soil on that side as well. So we'll call that good enough. At this point, we will change our units to pounds and inches. That's just going to make it easier for me to enter the modulus of subgrade reaction because this is the form in which it was given. So for the top soil strata, we have 500 PCI. So enter that. Now we have some soil springs. Our next soil strata has a K of 100. Next one beyond that is 500 and 500 for both directions. And the bottom soil strata is 2,000 pounds per cubic inch. All right, so now we have the soil springs entered appropriately using an elastic type soil spring. And just kind of a side note, as I was looking through here, I could tell where the boundaries were between the soil strata just by looking at the node numbers. So 1 and 2 are obviously different from everything else in here. But then we come down, 69 is a decent jump from 77 because these elements were created after this was. So I'm able to tell at this level that's where one of the soil strata is. Then it can come from here, from node 70, looking for node 71, so that's the bottom of the next layer. So, nothing too crazy there, but just something to make it a little easier getting through that. I will now do the same thing at Pier 2. I've ended up using the same soil profile, but it goes deeper because we have higher loads on the interior 2 piers. So let's see. Come back out here, copy. We'll get back into feet. All right, so I'm going to copy those nodes down 10.2 feet. Next layer is 14 feet thick. Where'd we go? Next layer is 8 feet. Next layer is 11.8. Oops. 11.8. And next layer is 5. And finally, 13 is the final layer we're going to be looking at. We're looking at a 62-foot caisson depth, so that matches with what's expected, so I guess I entered it right. So let's see, at this point I'll go ahead and just define the nodes for the other caissons as well. The soil profile was different as we got out towards Pier 3 here, so that will be entered differently. So we have 9.5 feet for the top layer, 27 feet for the next layer, 7.5 feet for that layer, 5 feet, and 12 feet. And finally we come along here to Pier 4. Different yet again. So 14.1 feet from the top of the caisson down to the extents of the first soil layer. And then 8.9 from there, 11.8 from there, and 9.2 from there. Cool, so we have our nodes. Now we can go ahead and throw the caissons in. Create element, left off, I guess it stayed where we left off. Grade, I guess 4K site concrete with the caisson cross section. Alright, so those are all created. Now we're going to split it up like we did last time and apply the soil springs. So I'm going to divide the element, 4 divisions for the top layer, 5 for the next layer, 3 for the next, 4 for this layer, 2 for this little small layer, and 4 for the bottom layer. Again, we're going to come out to boundary. Let's see. We need to make sure that we have some vertical support in here. So we're going to put those rigid supports in on the bottom nodes at piers 2, 3, and 4, as we did at Pier 1. And now we're going to go to our surface spring. Make sure our settings are where they need to be. Going to make sure we're applying it to a frame with a width of 4 feet using linear elements, or linear springs rather. And need to change my units. So now we can come in here and define our soil. Next layer is 100 PCI for that elastic modulus of subgrade reaction. 105, here we go. Next layer is stiffer, got 500 pounds per cubic inch. 6, 7. Next layer is quite a bit stiffer. I have 2,000 PCF. This little short layer here is relatively flexible, I guess. We have 225 PCI. And in the bottom layer, we're back to 2,000 PCI. Okay, well at this point I'll fast forward a little bit. You've seen it done a couple of times. So, you know, I would split up these large elements into similarly sized smaller elements. The smaller you make your elements, the more, I guess, precise your numbers are going to come out. You're going to be able to more closely hit the maximum values for shear and moment within the caisson. but it ends up, I guess, in this type of model where there's not a whole lot going on, runtime's not a very big issue. But if you had a very large model, like if you decide to model superstructure using plate elements or something, it may take a fair amount of time, just the more elements you're adding. So it's always a trade-off as to what your element size are. I think I'm using 2 or 3 feet per element through here. All right, so like I said, I'll fast forward and skip to a model that has the caissons and the boundary conditions entered already. Just make sure I'm looking at what I think I am. Take a look at the supports. Those are in there. Take a look at the surface springs. Oh, I'm sorry, let's see, point springs. And those are all in place. All right, so at this point we have our entire substructures defined. So that includes the pier caps, columns, and caissons. So let's clear those so they're not kind of in our way. What we do need is our superstructure. So we found that we were 2.77 feet from the calculations that the program did based on the superstructure, or the cross-section that I entered. So we're going to be at an elevation of whatever this is. I think it's 16 feet. Plus a foot to get to the top of this, plus 2.77 feet. That'll have the bottom of the superstructure sitting right on top of the pier cap here. So we can create some nodes. We'll create the first one at the near end of the bridge as we're looking at it here. So 0, it's going to be centered, so y is equal to 0. And z is equal to 19.77, I do believe. All right, 19.77. To see that element, we've got to rotate things a little bit. We'll grab that and copy it 7 feet ahead. We'll grab the one we just created, copy it 61 feet ahead, and we're just going to try to hit, or we're going to hit the just above the center of each of these piers. So next one is 63.66 feet, 0, 0. Oops. Got to select the node first, then we can copy it. And then we'll go 61 feet from there to get above Pier 4, and another 7 feet to get to the other end of the bridge. Now we can create, where am I at? We're going to create our element for the superstructure. We're going to use the 5 KSI concrete and our Flume cross-section from here to here. So there's that. We want to connect the superstructure to the substructure. So we'll get in a view where we can see what we're doing. So a little further. All right, so here's the node for the superstructure. Here's the node for the pier cap. I'm just going to put in an elastic link that's essentially rigid for all 3 translational degrees of freedom and free to rotate in all 3 degrees of freedom. So as our boundary, we're going to put in an elastic link. Just put in, change our units to kips, put in a very large number here, so 100,000 kips per foot get us close enough to a behavior where we're fixed for translation and free to rotate. So we can put that boundary condition in from the superstructure to the center of the pier cap at pier 1. Again here, at pier 2, at pier 3, and at pier 4. Now we can divide up the superstructure into, I guess, more manageable pieces and more, I guess, more realistic element sizes. So we're gonna use about 3-foot long elements. Again, this is a small structure, so having a lot of elements isn't that big a deal. It's probably a little excessive having 20 points on this thing, which is what I'm going to do for the longer spans, but it works. So we're going to divide these end pieces, those little 7-foot cantilevers, by 2, so that gives us 3.5-foot long elements there. These 61-foot long spans I'm going to divide into 20. The middle span is going to divide into 21 since it's a hair longer. Alright, so there's that. It's a bridge. It's going to experience some loads, so we'll go ahead and set that up. So self-weight, I'm sorry, first we're going to make some load cases. So we'll have dead load, which is permanent. I'm going to call it DC. We're using LRFD. We have, I'll put in the wind load. It's real quick and dirty like. Wind on structure. And thermal. Alright, so we have our load cases created. Now we need to populate those load cases. So we can create the self-weight, putting a -1 in the z direction. That means gravity is acting in the negative z direction. That's typical. And make sure that we are putting that into dead loads. Done. Alright, so now we can put wind load on. That is going to be under wind load case. Make sure we're using kips per foot. I pre-calculated the force that's going into there as 400 pounds per foot acting transversely. So that's going to act in the global y direction. 0, I guess using the relative input, 0 just means from where you start. 1 means where you're ending. Alright, so we'll rotate this a hair, make sure we're applying it to the full length of the superstructure. So now we have a transverse wind load. We're also going to have a small or longitudinal load of 0.096, so 96 pounds per foot, starting here to here. Alright, so that's our longitudinal wind. The other thing is thermal. So temperature and pre-stress. We're going to set our system temperature to something that's not 0 degrees Fahrenheit. So we'll call it, I don't know, 50. And then we will apply a temperature change to the superstructure. So element temperature. It's going to start at 50. We're going to have, we're going to enter a 70-degree temperature increase. So grab all of those elements and make sure we didn't grab anything else. All right, yes, so that is our superstructure. We're going to apply final temperature of 120 degrees just to give us a 70-degree temperature swing. And those red dots indicate that's done. So now we should be able to hit run and get some results. All right, so that just took a couple seconds. We can, let's see, did I do this already? Yes. All right, something I did but didn't show is put these peers into what MIDAS calls structure groups. When you do that, then you can isolate whatever portion of the bridge you're wanting to look at. So this is peer 2. It's the case on column and peer count for peer 2. And you can activate peer 3 and peer 4. We can activate the whole bridge, like so. And we can deactivate the substructure, so we can put our superstructure into its structure group. So that's that. So now we have that all worked out. We can take a look at our whole bridge and start looking at our results. We'll take a straight-on view and look at our deformation under the thermal loading. So we can look at the values. Darn. Okay. When I was putting in my thermal loads, I accidentally put them into, I guess, entered them as wind load case. So that's easy enough to clean up. We can just come to load tables, go to element temperatures, correct one of these to make it into the thermal load case, copy that, and paste it all the way down. All right, so now run our program again, and we can get results, deformations under thermal. Just do dx with values. So here we can see that, I guess if we get close enough we can see. All right, so we can see that our structure acted the way that I predicted it to, the way I expected it to, because we have a stiffer soil profile out for piers 1 and 2 than we do for piers 2 and 3. So as a result, our point of zero thermal movement is right about here. We can get a little finer by using inches as our unit, and we're minus 0.011 inches to the left at this node, and 0.001 inches to the right at this node. So our point of zero thermal movement is right about here. You could interpolate between these two values and determine what it is more precisely if you needed to. But with that knowledge, you can then determine what the distance from the point of zero thermal movement to each of your substructure elements is. Then I guess that's less necessary here because we have our entire superstructure in place. So we can just say that our expected thermal movement is about 0.35 inches on this side of the bridge, and about just shy of half an inch on the other end of the bridge. And then each of these piers is moving some amount. This little conglomeration of values here should all be about the same. And that just tells you how much deflection you can expect in each of your substructure elements at the top of the element. We can also take a quick look at our beam forces under wind load. We'll just look at one pier and get rid of values. So let's see, maybe let's look at pier 1. under thermal instead. That gives us a better feel for how the program is handling the soil structure interaction. So we come in here. This looks like what you should kind of expect. So our moment is varying linearly from the top of the column to the bottom of the column, and then it's increasing a little bit as we get below ground. So we take a look at the nodes. Node 1 here is the bottom of our column, and then out here we're getting below ground where the soil structure interaction is taking place. So, it should be a familiar looking curve. After running a few of these peer designs, we can also take a look at shear. Get rid of those numbers. And similarly, it gives about what you would expect for that. One thing that I was asked to kind of demonstrate real quick from the MIDAS folk was post-processing. So let's see, we'll say peer 2, activate. What I like to do before I throw this stuff into a spreadsheet is make the node and member numbers, I guess, kind of meaningful. So you can hit the renumber element. You can renumber the node and element. Here you're putting in the start node and start element numbers. And I want to renumber this caisson and column. What that's going to do is allow me to define members 1 through whatever this one is when I go to the results tables. So here we'll do that. Peer 2 active. And we're going to do the same thing for this. Let's take a look at what our maximum number was. Maximum number is 27. So we'll start at 51 at the bottom of this caisson. Reason this other stuff is popping up is because those numbers are kind of being stolen from those other elements, and those other elements are being renumbered as what I'm doing here is being renumbered. So, all right, and then we can take a look at peer cap and renumber that. Let's see, we're node 77. Let's keep it under 100 when we end, so we'll go to node 81 and element 81. All right, so now that we have our nodes put together in a meaningful way, we're sequential from the bottom of this caisson to the top of this column. We can run our model again. All right, didn't really like it when I did that. Really would go through and do all of your caissons and your substructure, making all of the numbers more rational in that way. And that would speed up the runtime, because right now, the number, I don't know, number 70 is sitting next to number 200, and that kind of messes with your matrices as the program runs. All right, but as you do this, once we have finished running the program, we're going to go to the Results tab. We're going to go to Tables, and we're going to create a table that indicates what our forces are, and we can do our deflections as well along the height of the caisson and column system. Similarly, sort of, with the peer cap, we're not going quite in line because we're going from 81 to node 26, and then we're sequential again. But if you know that, it simplifies things. All right. Let's let this run for a second. I'm sorry. We're running right to the end of our time, but I promise this will be done in a second, and I can kind of show you how this dumps into a spreadsheet. So give it another second too. One thing I didn't mention much as we were going through here is that you can have varying degrees of, I guess, levels of analysis using MIDAS Civil to perform the soil structure interaction. So what I'm doing is kind of the simplest thing. It's assuming some elastic constant for each of our soil layers and turning that into a node spring. You could perform, I guess, a little more detailed analysis, determine what the nonlinear behavior of the soil is, and use a multilinear spring to define that. And that would just kind of give you better accuracy if that's required for your project. And all right, so now I can take my beam forces. I want members 1 through 25. I'm just going to look at this one column in caisson in our results table. So 1 to 25, and what the hey, we'll just include all of them. We'll include the I node and the J node. If you're looking at moments, it can be helpful just to unclick either the I or the J node. I guess we will do that. I'll just plot moment along the length of this thing. So you can include only one node per element. What that's going to do is, here, we can grab that and jump into Excel. So here's our data. So this is the member, load case, node. This is axial. This is, I'm sorry, 1 second please. All right, so axial force, this is shear 1, shear 2, torsion, moment 1, moment 2. I'm just calling it 1 and 2. You know, you look through your data, you'll know what's what. So don't need to go through too much detail there. All right. So now we have a table that gives us all the forces along the length of the caisson and the column. We can come into MIDAS here and use our node table to determine what the depth is of each of these nodes. Oops, darn. So from 62 up to the top is at 16 feet. So we can copy that, put that here, and then let's see, did it not renumber my nodes? Okay, yeah, looks like it did. And then, oh, but it did not renumber my elements like I meant for it to do. But, all right, I'm sorry. Had I done that, I would have, you know, elements numbers from 1 to about 25 up here. Node numbers from 1 to 26. And I could use that knowledge to plot what's going on with the in the system. So as it is now, we'll see if it works out. So we can get our moment with respect to depth. That didn't work out. But I hope you can see what I'm saying. Did I do a different peer? Okay. So, all right. Sorry about that. But if you go through that process, and I guess if you're a little more careful, by renumbering those nodes and elements, it makes it quite a bit simpler to do your post-processing. So you can make plots, make sure everything makes sense. You can grab out max and min and all the other information that you would like to have for your within your to use your data. So at that point, that just about concludes everything that I was going to show y'all.